Hello and welcome to Earthquake Tip number 26. My name is Shailesh Kumar Agarwal, Executive Director of BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces through 32 earthquake tips, which are authored by Professor C.V.R. Murthy, mentored by Professor Sudhir Kumar Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these tips, our aim is to spread right technical information in simple to understand language to our professionals who are in the field designing and constructing structures, especially our art. But before we start, let's make a pledge that any new structure we design or build must be earthquake resistant. This earthquake tip number 26 will explain you what harms load paths in buildings. Having understood the importance and requirements of load paths in earlier tip, let's get deeper into load paths in buildings. Let us first take most common types of RCC buildings with moment resisting frames or MRF, as you can see in this figure 1. A smooth transfer of inertia forces in a moment resisting frame is critically dependent on the geometry of the frame grid. Some of the desirable features of a frame grid include: number 1, several distinct planar and regular moment resisting frames placed parallel to each other in each of two perpendicular planned directions of building. Columns should run through full height and beams through full width of building. Thirdly, uniform spacing between parallel planar moment resisting frames in each planned direction. Fourth, beams with each planar frame should be slender enough to deform in flexure. Concrete beams of very short span may damage in shear, which is undesirable. Having understood these desirable features, let me explain this through this figure 1A and 1B, which shows poor frame grid. For smooth load transfer in moment resisting frame, it is necessary for beams and columns to intersect and to form a well-defined grid. As you can see in this figure 1A, the building has regular frame in both plan direction, that is in X direction as well as in Y direction. While in figure 1B, the building has irregular beams and columns layout consisting of small MRF in X direction as shown in this picture, left picture of 1B, and limited frame action in Y direction as shown in this right hand side picture of 1B. This is not acceptable for earthquake resistant design. Remember, as I told you in previous tip, large detours in load paths result in stress concentration in the frame and in poor performance. This will happen with frame lines discontinuous and if beam frames into each other instead of columns. Now let's understand discontinuity in vertical elements through this figure 2. Discontinuing a load carrying member along its length or height is harmful to earthquake performance of the building. As you can see in this figure 2A, it is not desirable to discontinue a column in a lower story of a building. Such columns are called floating columns and to be avoided. When a column is pushed out of vertical line in a lower story, as you can see in this figure 2B, the forces carried by the upper portions of the columns have to bend at the setback locations to continue towards the foundation. Such columns are called setback columns and not desirable. Presence of setback columns lead to poor building performance in an earthquake. Also, brittle damage is expected in beam column joints and beam adjoining the setback locations. Now let's understand buildings with structural walls. Structural walls are also called shear walls as they have large stiffness and little strength in the length direction and provide very good load path. As told you in earlier tip, the buildings with shear walls perform well during past earthquakes. Some of the desirable features of buildings with shear walls include continuous shear walls running through full building height, generally offer direct load path for inertia forces collected from horizontal diaphragms at different floor levels to be carried down to the foundation. Uniformly distributed shear walls in both plan directions, sufficient wall density, that means total cross-sectional area of these walls in plan as percentage of plan area of buildings. Now let's look at this figure number 3, which explains you the situations when departure occurs from these desirable features. Large or irregular opening, as you can see in figure 3, walls with smaller and uniform openings behave better, whereas shear walls with large and random openings, as you see in this figure 3b, have multiple load paths, and each of those has long detours. As a result, load path become long and convoluted instead of short and direct. This situation creates undesirable interrupted load transfer along the shear wall height. Design codes give special emphasis in design and detailing of walls between openings so as to reduce negative effects of openings and ensure desirable ductile behavior of buildings with shear walls. The other departure could be the discontinuity, out of plane offsets in lower elevations. This, let me explain you through this figure. Sometimes in lower story of a building, shear walls are discontinued completely, as you can see in this figure 5A. 5B shows where shear wall is discontinued and moved in plane, whereas figure 5C shows shear wall is discontinued and moved out of plane. It can be better understood by this figure 4 as well. Figure 4A shows discontinuity in the lower story. Figure 4B shows the discontinuity in the same plane, whereas figure 4C shows discontinuity out of plane. These situations lead to abrupt change in the load path, as you see through these figures, and buildings with such wall configurations perform poorly in earthquake and hence to be avoided. The next situation can be explained through this figure 6, where structural walls in upper elevations are truncated when shear walls are discontinued over a part of their width, as shown in this figure 6A, or over the full width as shown in figure 6B. Abrupt changes occur in stiffness and strength of a building within vertical plane. This practice should also be avoided in earthquake resistant buildings. This is all about earthquake tip number 26. Next earthquake tip, that is tip number 27, will be on how can non-structural elements be protected against earthquakes. Thank you.